All right, let's look at a trig example.
That's your actual value. That's your actual value, right? I like how you're just sitting there. No, it's not me. I thought it was in my backpack, so I was like. Oh, wait, is it not hot enough? Like, wait, don't touch my yeah, exactly.
Okay, let's have a look. Have a look. Okay, so we're not going to graph this one, right? We're just going to do this based on the method we used yesterday, right? We're going to create a table. So we've got our X row. We've got our, in this case, G. And I'm going to add G prime. So the endpoints are at X equals on the left, pi over 6, and on the right at pi thirds. And we're trying to find absolute extrema, right? So where can those occur? Okay, at endpoints, or what do we call those? No, what do we call those values of X where? Critical numbers. There you go. Good, so we got to find the critical numbers. Now, in our search for critical numbers are related to the first derivative. So critical numbers are located where the first derivative is either, what's one thing? 0 or undefined. Good. Okay, so what's our derivative here? It's the derivative of cosecant. No. Negative cosecant. Oh, we should know this. Cotangent. Good. Negative cosecant x, cotangent x, right? Okay, so then we need to ask ourselves, where is this function equal to 0 and where is it undefined? That's a really inconvenient way of writing it, though, because we're not as familiar with cosecants and cotangents. So what do you think we ought to probably do with that answer? Okay, let's write it in terms of sines and cosines, right? So this is going to look like cosecant is 1 over sine, right? Cotangent is cosine over sine. So isn't this just negative cosine x over sine squared x? Okay? That's convenient because that looks like a fraction. And so when we're looking for our two different types of critical numbers, the derivative g prime of x, then let's write this down. This is really kind of a cool thing to do, and it makes life easier in math. So we'd say g prime of x equals 0 when what simple equation could I write? When what is true? Good, when the numerator equals 0, right? Which is when cosine x or negative, same thing, negative cosine x equals 0, right? So that's true when the numerator is 0. I can put a negative sign if I want to, right? G prime of x is undefined when what? Sine squared x equals 0, right? Okay, so where do those things happen? So cosine x equals 0. This is just really a unit circle question, isn't it? Where does cosine x equals 0? Cosine is the x or y coordinate on the unit circle. X. Okay, pi over 2, 3 pi over 2, etc. There's an infinite number of possibilities, but remember what our domain is. We're going from pi over 6 to pi over 3.
So it's pi over 2.
Pi over 2, does that fall in that interval? It doesn't, does it? So as far as we're concerned, there are no places on our function where the first derivative is equal to 0, right? So we don't get, so none of those. Those, nowhere for us. Okay, where is it undefined? Okay, it's undefined when sine x equals 0. Where does sine x equal 0? 0, pi, 2 pi, etc. So does that happen anywhere on our interval? No. So do we have any critical numbers on our interval? No. There are no critical numbers. And so what's the only thing we really need to do here to find our absolute extrema? Yeah, just compare the value of the function at the endpoints, right? So the value here is going to be, well, what is the cosecant of pi over 6? What's the sine of pi over 6? One over 2. Yeah. Right? So the cosecant of pi over 6 is 1/2. I mean, sine is, sorry. So the cosecant is the reciprocal. So it's 2. Right? So there's 1 point. What about at pi thirds? The sine of pi thirds is what, Zoe? Square root of 3 over 2. So the reciprocal is 2 over the square root of 3. Right? Or 2 square root of 3 over 3 if we want to rationalize that. Okay, which is bigger? 2 is bigger. So what's that? That's our absolute maximum, right? That's our absolute minimum. Okay? Absolutely. There you go. Okay? I know there's not a bigger because the only way there could be a bigger value is if there were a peak in between somewhere, and there can't be because there are no critical numbers. Remember that relative extrema can only occur at critical numbers. So if there are none, there are no relative extrema, right? Okay, let's look at maybe one more that doesn't work out quite like that. Yep.
I kind of follow that, but I don't get how to relate that to number 5.
Number 5?
Yeah.
Number 5 is the exact same problem, only it's a cosine. I'll do another one though, so we get.
I have it set up like different.
Well, let's do one like it. I'll do this. I'll do one similar to it. How's this? I don't want to do the exact one though. Okay, I'll do this. Hey, if we write that, what is that implying? That's really lazy. Like the book, the good book did that. What does that mean? Where are the implied parentheses? Yeah. Okay. And our interval this time, let's make this one. Hang on. What does yours do? It goes from. Okay. Okay, let's go from okay, how about that? Find the absolute extrema. So what's our derivative? Okay, negative pi sine pi x, right? Everybody agree? Okay. Because chain rule, derivative of cosine of hand is negative sine of hand times the derivative of hand is pi.
So normally would the pi go on the other side?
Well, yeah, but the pi, it would, but then we always want to pull the constants out front. Pi's the constant.
There was no pi, it would just be negative sine.
Yep. Yep. Okay, so let's look then at. So let's look for critical numbers. Are there any places where the derivative, negative pi times sine of pi over x, or pi x, is undefined?
No.
No. A sine function, how do you know that? Let's talk real quick. Somebody justify that statement.
Because there's nowhere where it's like there's like not an X on the bottom.
Okay,
Or
good,
it's not-
because there's not an X on the bottom, but with trig functions, you have to be a little bit careful, right? Now, for example, if we had tangent, let's say the derivative, it's not, but pretend it was tangent of X. Tangent is a compound trig function. It's equal to sine over cosine, right?
So you can change it to that and you would say one's defined.
Right, exactly. And if we did that, then there would be an X on the bottom inside the cosine function, right? Does that make sense? Okay, and so a better way of saying that is cosine, the value on the bottom the cosine X could be 0, which would cause problems. But sine by itself or cosine by itself is fine. Think of what a graph of sine or cosine looks like. It's just a wave that goes on forever in either direction. Are there any asymptotes or weird things? No, it's just a regular old function that goes on forever. No matter what value I put in, I'm never going to get back something bizarre, right? So we know that because this is just a constant times a sine function, it's well behaved. It's not going to, there are no places where it's undefined. So we don't get any of those, but we may get some cases where it equals 0 on our interval, right? The derivative. So we got to answer the question then, where does our first derivative equal 0? So let's just solve that equation. Right now we've got this trig equation to solve. So what do I do to both sides?
Divide by negative pi.
Divide by negative pi. And really all I'm doing is answering the question once again on the unit circle, where does sine of hand equal 0? Right? So let's look at our unit circle. Where is a sine function equal to 0 again? Say it again.
Pi.
This is pi or 0 or 2 pi or whatever, right? Okay. So integer multiples of pi, right? Okay. So then we know that sine of pi x equals 0 when pi x, right? Whatever we're taking the sine of, we'd say the argument of the sine is equal to some constant, let's just call it n times pi, right? It could be 0 pi, it could be 1 pi, it could be 9 pi, it could be negative 3 pi.
Then
So
do n and x equal each other?
n is an integer. So what does that tell us then? Let's look at this result. If I know that x times pi equals n times pi, I can divide both sides by pi, right? Agreed?
Yeah.
Okay, so if I do that, I get the result x equals n, but what does n represent again? Any integer. So our critical numbers are going to be at any integer value of x, right? So what integers fall in our domain? We're going from negative 7/3, which is as a mixed number is what?
2 and 1/3.
2 and 1/3?
Yeah.
So I'm going from negative 2 and 1/3 to negative 1. What integers are captured in that domain then? Negative 2, right? So that's the only critical number that we get that's not at an endpoint, right? So our endpoints look like this. This is supposed to be an open or a closed interval, sorry. So we're going from negative 7/3 up to negative 1, and inside that, at negative 2, we have a critical number, right? So those are the places we need to check. Negative 1 is also an integer. Is that such an important one, though? Well, no, because we're already checking that value, right? It's an endpoint.
Why would that not be?
It's not, what we're really doing is we're looking for our critical numbers. Let me
An integer that's all the same.
let me fix this real quick. So
Because there's
we're looking for all absolute extrema on the closed interval. So what's that mean? That means we're going to look at the endpoints and anything on the internal interval or the open interval between the endpoints, right? So negative 1, we're already checking it. It's an endpoint. But do we have anything between the endpoints that we need to check? Yeah, negative 2, right?
I don't get where you got negative 2 from.
Okay, I got negative 2 because that's a solution to this equation.
How?
The sine of pi x times pi, or pi x equals 0 when x equals 2, or 1, or 3, or -2, or negative,
Okay.
see what I'm saying?
So why
So
isn't it,
negative 2, 0, and 1 are the only ones in the
why isn't it -1?
Oh, no,
'Cause-
just 2 and negative 1.
Right, the only one in the domain that's within the domain, on the open interval between the endpoints is -2, right?
Not negative pi.
Well, no, because we're multiplying x times pi. So the values of x would be like, where is sine equal to 0 at the integer multiples of pi, right?
Okay.
So that just means that if x is any integer, right, this quantity is going to have a value of 0,
Okay.
right? How did we get that algebraically? Do you see how we got that out? I mean, we just said, okay, this is something you guys haven't done a lot, but we just said, okay, that means that whatever we're taking the sine of, the angle, or the argument of sine, if it equals any integer multiple of pi, so we just plugged in an n, where n really represents the set of all integers, right?
Is this in radians or?
This is in radians. Yeah.
Okay.
Okay, make sense? So how do we show this on our table? This is kind of cool. This is the first glimpse of what we're going to do in the future with our table. We can actually use this f prime row. We're not using it for much, but right here we could make that a 0. Why is that important? Because a 0 first derivative means a critical number, right? So we might put Cn above that to denote that it's a critical number. You get that? How this organizes everything? And then what do? We just check the values there, and there, and compare the results.
Yeah.
The biggest of those 3 is our absolute maximum. The smallest of those 3 is our absolute minimum.
Okay.
Okay?
So, just real quick, now do we plug, how do we get the f row numbers again? I'm sorry.
So the f numbers, that's where we just go back to our original function and plug in values for x.
Okay, that's what I thought.
Okay. Make sense? Okay? Have at it.